All right. Hello, everyone. Game plan for today. We will quickly blast through this lecture and then we'll talk about the quiz since that's probably all you care about. And we'll write some kernel code and we'll do some fun stuff just to make things like crystal clear. All right. So today we'll talk about lock implementation. Last lecture, we tried a lock implementation and it didn't quite work, right? We showed an example where two threads can call lock and two threads can return from lock, and that is not a mutex, right? Two threads came, two threads went through. When in a mutex, it should only be one at a time. So you can implement locks in software with kind of minimal hardware support. The only two hardware requirements you actually need are atomic loads and stores, and you need instructions to execute in order, which sounds like a no-brainer, but processors today execute out of order, so that is not necessarily true nowadays, which kind of makes your life a pain. So if these two things are true and you want to implement locks with no other hardware support, you can use something called Peterson's algorithm or Lampard's bakery algorithm, which is essentially just if anyone's ever been to an old school like bakery where you just pick a number and then you're served in that order, that's pretty much what it is. And we'll see what the other class talks about in terms of doing this if they don't show hardware support. But for now, we'll talk about real hardware support that you would need to implement locks. So they don't scale well, and you need special hardware support because now processors do execute out of order. Yeah?
How does it work if they execute out of order? What does that even mean?
So within your processor, right, you have instructions, and they're like they get split into micro instructions, and the hardware to make optimizations will reorder them if it can and do weird stuff like that.
But it still fundamentally keeps like if you needed to add and multiply, it wouldn't like swap it so it's multiply and add because that could be a different result.
Yeah, so it would reorder them such that you still get the same result, right? But internally it might, if we start caring about the details now in terms of data races and stuff, it might reorganize it where you'd still get the right result, but the details in between might be different, and that might cause us some issues. But in terms of hardware support, there is this kind of magical atomic function, so you can think of this function as atomic, so it either fully completes or it doesn't complete, and we'll call it compare and swap and give it a C API just to make it a bit clearer to read than assembly. So it's called compare and swap. It takes a pointer to an integer and then two integer values, an old value and a new value, and it returns whatever value that pointer points to. And why this is a useful function is it will only swap if the original value was old, and then it will change it to new. So that way, if we have compare and swap and we give it L with a 0 and a 1, there's only going to be two outcomes because this is atomic. Either compare and swap returns 0, which means it pointed at a 0, and you're guaranteed from using this function, that means that that 0 got swapped with a 1. So in only the case where compare and swap returns 0, then it will have changed that whatever it was pointed to from a 0 to a 1. And that's the only way to transition from 0 to 1. Otherwise, if it was already 1, compare and swap will return 1, which would make this loop go on and on and on again, right? So it would just keep on doing the compare and swap. The value would be 1. It would keep on looping, looping, looping until eventually the unlock happens and a 0 is written to it, and then another thread that was waiting at the lock could pass. So this is actually a valid implementation of a mutex. It is technically called a spin lock because, as you can see, this while loop just spins. It just tries over and over and over and over again, and it doesn't do anything very smart. And it also violates another rule that we wanted for mutexes, where things are fair. Because in this case, if everything's just fighting over the lock, you've no control over what thread actually gets the lock, and it could be that the same thread just by virtue of context switching and whatever the kernel decides the schedule can be, it can just be one thread that gets the lock over and over again, when technically you should share it. So that was essentially spin lock, and compare and swap is actually a very common atomic hardware instruction. On x86, it's called compstinge, which is a sick shortening, right? So all that says it's called compare and exchange instead of compare and swap. Don't ask me why they cut so many letters, so it saves them some typing, I guess. But that's a valid implementation of a lock, but it still has a busy wait problem, and it's not the greatest implementation.
There's no like actual like C function for this, right? This is how is this assumption look, right?
Yeah, there's a C function for it, but I think it's also called compstinge, which is less readable. I just called it compare and swap, so it's a bit more readable. But yeah, so if you consider a uniprocessor system, so something with only a single CPU core on it, we know we're definitely wasting our time. Like if I can't get the lock here and I'm the only thread that's allowed to run, if I see a 1, nothing else would have changed it to 0. So I'm just kind of endlessly spinning for no good reason, even though I should know better at that point that I cannot acquire the lock. So a better thing to do would just be to let the kernel schedule another process or another thread in the hopes that that frees the lock. So you are going to implement this in lab 2, that's your yield. So instead, if you see you don't get the lock, you could just simply yield and then hope another thread frees it up for you. And then on a multiprocessor machine, it depends. You might want to have a spin lock if you want to be super responsive and you know your critical section is very, very small. It might actually be more efficient to just spin a few times as opposed to putting a thread, yielding a thread and then waiting for it to come back. So this is what it looks like if you add a yield. It doesn't complicate the code that much. It's just if we see that we didn't successfully compare and swap, which means the lock is still locked, we just yield. But now this has we kind of eliminated the busy wait problem, but now we have what's called a thundering herd problem, where if we had 8 threads that came here and they all yielded, well, as soon as we unlock, we know only one of those 8 threads can acquire the lock after we unlock it. But what's actually going to happen in this case is the kernel is going to wake up all 8 threads at some point, and then they're all going to try to get the lock, even though we know 7 of them aren't going to succeed and only 1 is. And we still have the problem where we have no control over what thread gets the lock next. So ideally, we want to be able to reason about it, and the easiest thing to do is to just kind of have like a first in, first out queue. So you just, in order of when you try and acquire the lock is the order you actually get the lock. So we can change the implementation and we can add a wait queue. So now when we do the compare and swap and we see that the lock is acquired by another thread, we can go ahead and add this thread, this current thread, to a lock wait queue, and then we can put ourselves to sleep, which means we need another thread to wake us up. So in the unlock, we would unlock the lock and then check if there's any threads in the wait queue, because we need a thread to wake up if there's a thread waiting. If there's a thread in the wait queue, we would wake up one thread and it would be the thread that's at the front of the list. So hopefully we're nice and fair. But because we're now in the land of concurrency and difficult programming, there's actually 2 issues with this code, even though it looks kind of correct. One's called a lost wake up, and the other one is just called the wrong thread gets the lock. So let's have a look at it and see if anyone can tell me where my problems are. So looking at this code, first thing we'll try and identify is a lost wake up. And the lost wake up should mean that a thread gets put to sleep and it never gets woken up. And if you want to go with the real life analogy, the thread essentially gets put in a coma, which is not.
puts yourself into the queue.
So the comment above that puts itself into the queue.
I guess if you add yourself to the queue, but then you context switch right afterwards, and then like the other lock gets unlocked, and you pop yourself out the queue, and you come back, and then you go to sleep, and you just sleep forever.
So what thread 1 is like here, it added itself to the queue but hasn't slept yet?
Yeah, and then you like switch to the thread that's gonna unlock.
So thread 2 comes here, it goes here to here, so it unlocks.
And then it wakes up the first one, but it hasn't gone to sleep yet. Right?
Yeah, so that's one problem. So it would come in here, and then there's a thread in the wake queue that's not asleep yet, and then it would try and wake up. Although that's something you would check. You'd probably get, if you wanted to, you could check, some error code from the wake up, being like, oh, the thread's not asleep yet or something. But that's definitely a problem that we don't consider now, so that's one problem. What about the opposite, where I am asleep and I never get woken up again? Yeah.
Would that be like the same thing? So in this case, and then we go back to thread 1, and we execute thread sleep, but then we are not in a queue, so we go to sleep forever.
Yeah, well, that wouldn't happen though if here, let's see. If we had another condition here that's like if not asleep, try again. So then that would fix that. Yep.
If it went past the wake up before it added itself to the queue.
So you mean like if thread 1, whoops, what the hell did I just do? No. So if thread 1, instead of being context switched there, it got context switched there. Yeah. So, and this also assumes that thread 2 has a lock and it's calling unlock. So we would assume thread 2 already has the lock, and then thread 1 comes into the lock function. It would try the while loop, compare and swap would return 1. So that means the lock's already acquired, and we just said thread 2 has it. So it would go into the while loop, and it might get context switched out immediately before it adds it to the queue. And then thread 2 could go ahead and unlock itself. So it would set the lock to 0 and then check if there's any threads in the queue. There currently is not a thread in the queue, so it wouldn't bother waking up any thread, and it would just return. And then we would get context switched back to thread 1, and then thread 1 would add itself to the queue and be put to sleep. And now no one is going to wake it up because no one is going to call unlock, right? You need to pair lock with unlock. It could be woken up if someone calls lock and unlock, but that would also might add another thread to the queue, in which case you wouldn't clear the queue. So you're missing a wake up. Yeah.
So we're missing it because the second thread, T2,
Yeah.
ends after exiting the unlock function.
Yeah.
Is that right?
Yeah.
So it can't execute anything else, it's over.
Yep.
Okay.
Yeah. So it's all done. So does that make sense? So, all right. How would we fix this? Oh, wait. No, we still have another problem to go over. So that's lost wake up. Can anyone think of a case where we have say we have 3 threads. Here, I'll make it a bit easier. Say we have 3 threads. Actually, well, that can still be there. 3 threads. T1 has the lock, and then T2 is in wait queue. So if that is our beginning assumption, can anyone tell me a case where some rogue thread to come in that it is not in line and essentially bypass the line? Yeah. Yeah, so right now, if T2 is in the wait queue, the next thread that should get the lock is T2. So assume we have another thread called T3. So is there any way for thread 3 to get the lock before thread 2? Yeah.
Thread 1 unlocks, doesn't call the if, and then thread 3 comes into the lock and checks it.
Yeah, so thread 1 has the lock already, so it would be the one responsible for calling unlock. So at this point, it would be, say thread 1 is here, it's called unlock, and then it goes ahead and changes that value from a 0 to a 1, and then it gets context switched out right before the if statement. And if right before the if statement, thread 3 comes in, which is the new thread, and calls lock, it would see that the value of the lock is a 0. The compare and swap would return 0, which means it just grabbed the lock and it just swooped right in and took it, when it should have been thread 2's turn, right? It essentially got like the fast pass at Disneyland without paying for it, which Mickey Mouse does not like that. So does that make sense, that they can still bypass the queue? All right, cool. So let's fix that. So here's an example, just so you have it, of the lost wake up, which is slightly different than what we just kind of discussed, and then the wrong thread getting the lock, just so you have it. So here's how you would fix that problem. It's kind of big, it's ugly, and we will go through it quickly. I'll get myself out of the way. Okay, so to do this, we are going to use essentially 2 locks. So there is lock, which is what we want to represent the entire mutex. And then we're going to have a second lock called guard that we only use internally. And guard, we will use our spin lock implementation because we know it works. And this is the only place we'll use that guard lock, so we know the code is nice and short. So, you know, having a spin lock won't be that big of a detriment. Yeah.
For the lost wake up example, I just want to ask a quick question. So that case only happens if it's like 2 threads and then one thread just unlocks it, but the other one's still waiting for it, and then it puts itself to sleep. And then as long as another thread goes in, tries to lock and unlock, the one that went to sleep infinitely will wake up again, right? If nothing goes wrong.
So the lost wake up is only going to happen if that queue is empty, and it essentially skips that if statement when it knows another thread's about to be added. But yeah, you could not have a bug if there was something already there that was ahead of it. So, you know, there's a thread waiting anyways, and that thread would get waken up even if I haven't added myself to the queue yet. So likely you wouldn't see this bug ever, right? It's kind of a rare, it would only happen if the list is empty. Okay, so let's break down this quick because it kind of looks ugly. So whenever you see this compare and swap with the guard, you can replace that with, just think it's a spin lock, so just replace that with a lock to guard, and then here is an unlock to guard and unlock to guard. So we're locking it at the beginning of the function, and then there's 2 paths, and we unlock it in both paths. So we grab the guard lock, so everything until we unlock it is all, you know, only one thread can be there at a time, so we won't have any data races, which is what we which is what happened before. We got context switching and bad things happened. So in the case the lock isn't acquired, we don't need compare and swap anymore because now we have this guard and we're under mutual exclusion, so we're the only thread. So we don't need compare and swap anymore to actually acquire the lock. So we check if the lock is 0. If it's 0, we just change it to 1 because we're the only thread actually accessing it. and then that means we would acquire the mutex, and then we can unlock it, and then it would return. So that's a case where we don't have to do anything, we just immediately get the lock and it's all good. The other case where it is locked, we would add ourselves to the queue, throw ourselves at the back of the list, and then unlock the guard, and then put ourselves to sleep. And then in the unlock, here is essentially our lock to guard, and then we can check the queue because now if it was going to add itself to the queue, it would have already done that because it had the guard lock. So it wouldn't be able to jump from here to there because it would need a lock to actually execute this. It's in a critical section. So after the guard, we check if the queue is empty. And then if it's empty, we can just release the lock. We don't have to do anything. Otherwise, instead of even unlocking it, we can just keep it locked and just transfer it to the next thread because the wake up is going to transfer the lock here. We're just going to wake up a single thread, so it'll transfer here. The value of that lock will still be 1, indicating it's locked, and it'll just continue, and we'll be all good. So does that make sense to everyone? Yep.
How is the guard keeping things out? Like you said that it was like keeping it like protected or something?
Yeah, so the guard is like a mutex, right? It is a mutex, but it's a spin lock, so it behaves the exact same way. So like this is lock, this is unlock, this is unlock. So anything between the lock and unlock, only one thread can be there at a time. So we don't have any concurrency issues.
Okay. Except like in theory it could unlock it and then switch to something else before it puts itself to sleep. Right?
So, yeah, so there's a slight error, there's a slight bug here because we unlock here, and it could be the case where before we put ourselves to sleep, it gets context switched right at this point, and this can actually run now because it can acquire the guard, and then it would do a wake up on a thread that's not asleep yet, but that's actually a condition that you can check. So your wake up can be like, oh, that thread's not asleep yet.
So then you just loop that wake up.
Yeah, so in this case, there's a slight data race, but you can actually detect it. So if wake up fails, I know something is in the queue and it's about to put itself to sleep, and I got super, super unlucky. So if it's like the spin lock, right? If I just retry a few times, probably be fine. But yeah, there's still a slight data race, but that's like, even catching that, I didn't see it the first time. All right, that makes sense to everyone? Yep.
So, how does editor prevent other threads from jumping to the queue?
Sorry?
How does editor guard prevent the errors before messages?
So the guard is exactly a mutex, like what we saw yesterday. So only one thread's allowed there at a single time. Because this is essentially lock and then unlock. So if you have the thread and you are executing this line here, say you're executing this line here and you get context switched out, you acquired the guard, right? So no one else is in this code at all. They would just be essentially either here or there and trying to acquire the lock, and they couldn't get it. So it's just going to wait till you get context switched back to the original thread, and then it's going to continue executing.
Also, if you go through the loop and guard is 0, it means the guard is unlocked, so you turn it to 1, so you lock everyone else
Yeah.
from it, and then so no one else can access it.
Yeah. Yeah, so it's a mutex. So like this is a valid implementation of a mutex, right? And it only allows one thread between lock and unlock. And we're essentially just using this spin lock in this code. So we're using a spin lock as a guard to implement a smarter lock that will actually put the thread to sleep and do all that good stuff. So we eliminated that busy wait problem, right? We're just trying to solve all these problems. The lost wake up, the wrong thread getting the lock, and also the busy wake up, and we were trying to also be fair. So now we have a queue that works. You can't bypass the queue. you can't have a lost wake up. You have to retry. You might have like, it might be about to go to sleep, but you can retry that. And, and we put ourselves to sleep, right? Okay, so that's the actual implementation of a mutex that you'll see. I don't think you actually have to implement it, but that's essentially what a mutex is, which is kind of cool. So also the next thing I'll say is remember what causes a data race. So a data race is when there's two concurrent accesses to the same memory address, and at least one of them is a write, and the write is kind of the important part there. So if the source of the data race is the write, that means we could have as many readers as you want. You don't even need a mutex as long as nothing writes at the same time. So if you just, and it depends on your program. So you might have a program that writes very, very infrequently and then has a lot of readers. So ideally you'd like to be as parallel as possible. So if you can have as many readers as you want to permit that, right? If I use a mutex, if I just have a mutex in my arsenal, I would have to put a mutex around the read and the writes just so I don't have any concurrent accesses that could be a write. So what you can do is implement a lock that has different behaviors based off whether you're acquiring it for reading or writing. So there is something called a read-write lock. So with mutexes or spin locks, you just have to essentially just lock the data, even if you don't know if a write could happen, which is what I just talked about briefly. But you want reads to happen in parallel as long as there's no writes. So for a read-write thread, you separate out the locks, so there's going to be a lock specific for reading and a lock specific for writing. And the property you want is that multiple threads can hold a read lock, but only one thread at a time can hold a write lock, so that you don't have any data races, right? You eliminate that two concurrent access problem and make it back down to one. And the read-write lock would essentially wait for all the readers to be done until you can get exclusive access to that lock. So we would use the same idea of having a guard lock here. And essentially our guard lock, and this time I'm just using it as a lock, just assume it's like a mutex. I'm using the guard to essentially guard this integer reader value so I don't have any concurrent accesses. So this looks exactly like we're going to use it to keep track of the number of readers that are currently active. And this ++ reader sure looks like a lot like ++ count. And we don't want the same issues where we don't know the correct numbers, especially if we're actually managing a lock, because we also have a decrement. So in the case of the write version of the lock, we want it to essentially exactly be our original mutex. So write lock just calls lock, and write unlock calls unlock for our lock in that structure. And then the only difference comes for the read lock. So it would acquire the guard and then unlock the guard. So all of this code and all of this code, they're in critical sections that are protected by the same guard lock, so they can't run concurrently because we're changing n readers. So all it does is keep track of the number of readers. So it just increments the count that you would assume is initially 0. And then if it went from 0 readers to 1 reader, so this is the first reader, it would just try to acquire our lock. And then after it's done, it would unlock. And so now if another thread comes in and calls read lock again, it would just increment itself from 1 to 2. It wouldn't have to call lock again because we're just reusing that lock, right? It's still a mutex. If we called lock on an already locked lock, it's too many locks and it dies. So then our unlock, we would just decrement the number of readers, and then if we see that we're the last reader, we just do our normal unlock call. Yep, everyone good? Yep.
If the data race is only caused during the write, why do we need a read lock?
So you need the read lock because it acquires that lock. If you didn't have a read lock, all the reads could still happen, and a write could happen as well, and that's still a data race.
Oh, so we don't know, we
Yeah. Yeah, so this is, if there's one reader, it gets the lock, and then they can all share it, essentially. So either, there's like two versions of the lock. Either just the writer just has it like a mutex, and it's the only one with it, or one or more readers have the lock, and they're all sharing the same lock. Okay, this makes sense? Cool, all right, let's wrap up and talk about quiz stuff and have more fun. So you want critical sections that we talked about today and yesterday to protect against data races. You should know what they are. Very, very important, and even more important, how to prevent them. There are lots of fun bugs and lots of fun and interesting questions you can ask about them, because preventing them is very hard. So mutexes and spin locks are the most straightforward that we actually know how to implement now. Ideally, you need some hardware support to implement locks, and you need some kernel support for the wake-up notifications, or you actually have those, you're actually writing those yourselves in Lab 2. And then, you know, if you have a lot of readers, you have a read-write lock. All right, cool, let's talk about the quiz. So did anyone go on Quarkus? So everyone saw the micro quiz? Is anyone worried about it? Yeah? What? Okay, so let's quickly go over the micro quiz, because this will take us like 2 seconds. So question 1. Again, this wouldn't be valid because it has the word MMU on it. I don't know why he reads this one. But so on a context switch between two processes, the operating system has to modify the state in the MMU. To make this valid for you guys, it would be the operating system has to swap out address spaces. So is this true or false? True. Beauty. Question 2, or whoops, which is probably on the harder end of things for this. So when a divide by 0 in a program occurs, a trap instruction is invoked so the kernel can kill the program. True? False. Why?
The trap instruction leads to a system call.
Yeah, trap instruction is a system call. What's this actually called? An exception, which will generate a signal. So close. So that false. On a computer system with just one processor, there are no benefits to having multiple threads with one process.
False.
That better be false, otherwise you're all taking this course for no reason.
Wow.
All right, which of the following, so this might not actually be super valid, but it's like kind of general enough, but this is probably like the hardest question on this in terms of like knowing stuff from the lecture. Which of the following is responsible for translating a process's virtual memory address to physical memory address? Whoa. All right, the compiler, probably not. Operating system kernel, not technically, which is why this question is kind of odd. Hardware, technically yes, because the MMU is hardware and does it. Yeah, MMU is on the CPU, which will, yeah, so this is why the question's kind of weird, because it's like kind of classified as hardware, but so technically your kernel will set up essentially lookup tables for the MMU, which is why I don't want to talk about it yet, because knowing that it translates it doesn't really help anyone. So technically this answer is hardware. It's like one of the most silly questions on this, which is why this little micro quiz is probably actually harder than the actual quiz. You don't know that yet. Yeah, we haven't talked about that. It's like, yeah. So question 5, assume you have a computation such as matrix multiply that you would like to parallelize so the computation can be completed more quickly. You can do this by either using multiple threads within a process or by using multiple processes. To decide which of these two approaches you use, you consider various trade-offs. Which of the following considerations are valid? Select all that apply. So this is your multiple answer question. So using multi-processes will result in less physical memory needed. No. At best, it would be a wash or negligible, but it's not lower. All right. Using multiple processes will result in slower, more costly synchronization. Yes, because if you have separate processes, right, the only way they can talk to each other is through the kernel, which would have to be system calls, which is slower. All right, using multiple processes will result in faster data sharing. No. False, because I just said the first thing. All right, using multiple processes will result in higher context switching overhead. True, right? Because we don't know everything involved in context switching processes, but it's at least going to be the same thing as threads plus swapping the address space. So that's more, that's slower. All right, using multiple processes will result in fewer harder to detect bugs.
True.
We got a true, true.
I think that's true because you can separate the tasks.
Yeah, so that's actually kind of true because remember, if a thread dies and does like a segfault or something, whole process is going to die. You're not going to have any single clue as to where that came from. While if one of your processes dies, it won't kill the other one, and you'll at least have an idea about where it came from. So, yeah.
If they ask like an explanation, which is highly unlikely, but let's say this isn't like a short answer question, so could one possible explanation also be that threads work in shared space, which is why it's harder to debug which one went wrong?
Yeah, so another explanation is like, well, if you have processes, to link it back to the first one, to talk to each other, it goes through the kernel, so you can monitor that pretty easy. Well, if you share the same address space, it's a lot harder to see if you're walking over other things. Yep.
So which of these will still be true if the process was switched to threads? Like if you take all of the process and change it to threads?
So it's essentially just the opposite. So synchronization would be much faster, but it'd be harder to debug, and it'd be faster context switching. It's just the opposite of this. Yeah.
What do you mean by like synchronization? Can you like really a bit?
Synchronization, so any communication between the two processes, or like synchronization generally is involved with locks and stuff like that, and like making sure you do things in the right order, which we don't really know how to do yet. We kind of know how to prevent data races, but like locks and stuff aren't even on the quiz.
Right. So just how two things talk to each other.
Yeah. Yeah, so any communication has to be super explicit because it has to go through the kernel. Yeah.
What's the definition of context switching overhead?
Context switching overhead is just the amount of time it takes to context switch.
Switch processes or
Yeah, switch processes are threads. So it's going to be much faster to switch between threads than it is for processes, because processes would have to change the address space as well.
when we say result in higher context switching overhead, means it takes more time to switch between these processes.
Yeah, it takes more time to switch between two processes than it does to switch between two threads within a process.
Okay, thank you.
Yeah.
Question. So if you only have one CPU, let's say, and you're running a process, so it can you can still switch between threads within that process, right?
Yeah, well, if you have processes in this case, one process is just going to have one thread, right? If everything's a separate process.
Right. So really what I mean is, when does like the thread switching actually happen? Like, is it only switching when every time you wake up a process and then switch to the next thread?
So
Can you like while the process is still running, switch thread?
it depends if it's a kernel thread or a user thread. If it's a kernel thread, the kernel just decides. If it's a user thread, you get to decide. All right, let's submit our quiz and see how we did. Sick. We
Got it right.
yeah. What do you mean we got it right? You think I'm just going to go through and have them all wrong? 101 point, 101 point, 101 point, 101 point. Beauty, hundo. All right, more details about the quiz, just because I guess people like hearing about it. Open book. You can use any of your notes, lecture slides, textbooks. You apparently are not allowed to search the internet. You are not allowed to communicate with each other in any form or fashion or whatever. There's a room booked if you're worried about the internet and want a witness. It will be GB 304.
Wait, are we required to go there?
You are not required to be there, but benefit is I will be there. I can answer questions, but it'd be like a normal exam where hand up and I go over to you. I think Ashvin will also be on Zoom if you're not in that room. And then also benefit is if the internet in that room goes down, you have a valid witness. So if the internet goes down and everyone in that class can't do the quiz, yeah, you at least have a witness. So that might be good, or it might be somewhat fun. Probably not. Quiz format, it will be 15 true false, 5 multiple choice and 5 multiple answer with 2 short answer questions that are like between like max 3 sentences. If you write more than 3 sentences, you probably are like BSing and probably shouldn't do that. Yeah, PS, that's like a pet peeve of mine when I was a TA in marking. If you like just spew knowledge that you think is right but not relevant to the question, like that's a real crapshoot if your TA just doesn't like that or will show pity on you. I didn't show pity for that. Well, if you just dump knowledge for part marks that's not even relevant, you're just like wasting my time and your time. Yeah. Yeah, by default, when you make a process, it just has a single thread in it.
Like you can add more threads.
Yeah, yeah.
And that's not gonna make the total. Is that gonna make the total runtime faster?
Depends what your threads do.
Yeah, but like it's still like concurrent, not parallel, right?
If they're kernel threads and you have multiple CPUs, they can be run in parallel. Yeah, yeah. All right, cool. All right, to make things crystal clear, let's write some kernel code. Wait, it's actually not that hard. All right. Yeah, so this is not syscalls. I don't have to communicate with the kernel. We are now the kernel. So kernel code is not super different aside from a few things that are much different, if that makes sense. But the kernel code is just C code. It's C code, there's nothing special with it. So it has include files, so you include stuff from kernel, and there's a few macros. So you'll notice in this code that there's no such thing as a main function. This is my entire function. So there's not going to be a main because this isn't going to be an executable, because this isn't going to be a process, because this isn't going to run in user space. This is the kernel. Yeah, so processes are just user space things. So I am the kernel now, that's it. So there's not going to be a main because I'm not going to generate an executable because the kernel's already running at this point, right? I'm typing into my system, kernel's already here. So the way kernel code works, at least for like fairly modular things that you can throw into the kernel, is you make something called a module, and you can add code that executes whenever you load it and whenever you unload it. So this says whenever I'm loaded into the kernel, you should run a function called hello init, and whenever you're unloaded from the kernel, you should run a function called hello exit. So hello init, you'll see a few differences with C. So, or like normal C you've been written. This is not print F, this is print K. Anyone hazard a guess as to why? Yeah, do I have the C standard library in the kernel? No, because I am the kernel. So in the kernel, it's a bit different too. So it's essentially like an internal buffer just for logging purposes. So everyone's probably used logs before in some respect, or at least seen them. So there's different levels of messages you can run depending on how severe it is. So like you could have error messages, warning messages, debug messages, and so on. So I just said, hey, I'll put an info message just because it's nice to read. And I'll just print to the internal kernel buffer, hello init, and that's it. And then when I exit, I'm going to print hello exit. So if we go ahead and compile this, it's like it kind of is a C file, but it uses a bunch of kernel headers. And when you compile it, you'll see that it generates some kind of normal looking stuff. There's like a .c file, this .mod stuff that is super kernel specific. But generally you see if you compile it in little chunks, there's going to be like a .o file, right? We've seen .o files. But because it's a kernel, this is a .ko file, so which just stands for kernel object. So it's just indicating that you shouldn't probably use this unless you're using it with the kernel. So that's all you get. So you get this kernel module, and it is a normal ELF file, and the kernel knows what to do with it. So you might ask yourself, well, I have some code It's clearly not running because it's not executing at all. How do I even see it? So to insert it into a kernel, you use this command. So I have to use it as a super user, and it will install is just short for install module or insert module, however you want to think of it. So I'm going to insert hello.ko into the kernel, and then as soon as I insert it into the kernel, it will start running that hello init, and that's now going to be running in kernel mode. So I can do whatever I want. So if I insert that, oops, it says file exists because I tried it out before. Okay, we're going to see a bunch of messages. But if I insert it into the kernel, it now runs, and now I can see my debug messages if I use this command called dmessage. So that lets you read, and you'll never be tested on this. We're just exploring kernel mode. So you can use dmessage to see all the internal kernel messages, and then -L to see all the things that are at the info level. So if I do that, I called it a few times, and this is the latest one. So I can see that at this time, so everything's timestamped in the kernel, I loaded my hello init kernel module. All right, and then I could go ahead and remove the module from the kernel, and then run dmessage again, and I see hello exit. So now my code is no longer running in the kernel. Yeah.
This happened multiple times because you loaded and unloaded the program multiple times, right?
Yeah, so this was this morning's lecture. This was at the end of the lecture because I'll strace it for you to see what happens, and this was me just fixing it. And then this is right now.
Okay.
Yeah.
And so is the, sorry, what are the modules called? Are those like in the library functions? Like how does it know to like run it at the beginning or at end?
Yeah, so how does it know how to run it? So the kernel does a lot of like hacky things to make it work, but essentially if you include that linux.module and compile it with all the header files the Linux kernel understands, it defines these things called module init and module exit, which register functions to run whenever it's loaded into the kernel. So we can see that if anything executed, because we insert into the kernel, it has to be executing in kernel mode. So for example, if right here I can type code there and it runs in kernel mode and I can do whatever the hell I want. So if I knew the right functions to call, we could probably finally kill init if we really wanted to, because we are now the kernel and we can do whatever we want, right? And we can see even if we want, we can strace, sudo strace. We can see what install actually does because it shouldn't be too much of a mystery. If it's inserting itself into a kernel, the only way it can do that is if it makes a system call and says, hey kernel, please insert this into yourself and start executing. So if we strace it, we can actually see what's going on because we now know how to read it. So at some point, it opens that hello.ko file, gives it file descriptor 3, and we can see here that it is definitely an ELF file because we know what they begin with now. And then it does some other garbage where it fstats it, and then the important call is right here. Finit module gives it file descriptor 3, which is our kernel module, and then after that system call completes, the kernel is free to run that module as it sees fit. Yep.
Why is it a .ko file and not a .kc file? Like, isn't an object file like combined together to produce a C file?
No, so in a normal object file, your C file gets compiled to an object file, and then to make an executable, you combine a bunch of object files.
Right.
But object files are just machine code. They're compiled. Yeah. So it's just a .ko is kind of like a little piece of a library, right? I just defined hello init, hello exit, that's it. And I said, please run.
Run this because it's sudo, right?
What?
You're only able to run this because of sudo? Like you have
I'm only able to insert it into the kernel because it does some user checks to make sure you can actually protect that system call. All right, cool. We wrote some kernel code. So right now, if I wrote anything here, I can do whatever I want. I can screw up my kernel completely.
So if you like did a fork bomb, your entire computer would just get destroyed.
Better than a fork bomb, I can loop over all of my processes and just kill everything.
Like, how could you say that at that point?
What?
Would you have to delete and re-download the OS?
You'd have to reboot. Your kernel's going to die, so your system's going to die. So you're going to, if you power it back on again, it just reboots, right?
But that code will still run again, no? Because it's still inserted there and it runs every time it reboots up.
No. No, because I just inserted it.
Oh, it only runs when it gets inserted, not when it boots up, not when the kernel boots up.
Yeah, you have to insert the module.
Oh, okay.
Yeah. Yeah, you could.
That's so cool.
You could. Yeah, you could screw up your whole firmware if you want.